Hi, this is TheoryStation. I'm John Duggan, and the program we're doing right now is rational choice modeling. We're in the series Individual and Social Choice. This is installment 7 in the series. So in the last installment, we talked about a couple different voting rules. There's a bunch more that we could talk about, but we're focusing on majority voting and this Borda rule, which is based on points instead of pairwise votes. So in this installment, I want to continue thinking about these rules and then segue into what's called axiomatic analysis. We'll look at the axiomatic properties, some of the properties of these rules. So this installment will be, I'll call it Condorcet versus Borda. That's an overstatement, but Condorcet and Borda were 18th century contemporaries who were not professional, formal political theorists. I guess that didn't really exist back then, but they were people who thought deeply about voting, and Condorcet was interested in majority voting. That's where we get the term Condorcet winner or Condorcet loser. And Borda obviously was thinking about it in a different way. So we're not really having a contest here, but I want to just talk about some of the properties of these rules. So I guess I could mention a couple things in general that they both share. So both of these rules are based on the rankings of a set of individuals, and they don't favor one individual over another. In majority voting, one person, one vote is kind of the saying. With Borda, the points for one person count the same as the points for another person. So I'll just say in general, these rules they're both unbiased with respect to individuals. They're also unbiased with respect to alternatives, right? In majority voting or Borda, none of the alternatives have an inherent advantage over the others. So this property of being unbiased with respect to individuals, that can be formulated as an axiom. It's called anonymity. You don't have to know the names of anyone. You just need to know their preferences in order to implement these rules. And this property of being unbiased with respect to alternatives, that can be formulated as an axiom, and it's called neutrality. So these rules are both neutral with respect to alternatives. So, I mean, they have other properties, but let me go further and kind of home in on each one. Let's start with majority voting. So I already mentioned the idea of a Condorcet winner, and that's a good term to know. There's a related concept, though, that I want to talk about. To be choosable by majority rule, an alternative, really the key property is that it's unbeaten. There's no other alternative that beats it. Being a Condorcet winner certainly satisfies that criterion, but it's stronger because a Condorcet winner actually beats everything. So let me just put these two conditions side by side because they might sound very similar, and I'll illustrate the difference. So Condorcet winner is defined as an alternative X such that for every other alternative, X beats that alternative. There's another idea, though, that's related. And actually, I think I'll just adjust the way I'm writing this. I'll say X is a Condorcet winner if it has this property. Now, there's another idea. It's called the majority core. And of course, if there is a Condorcet winner, there can only be one, right? This other idea called the majority core actually allows for a set of alternatives. So there doesn't have to be just one. The property defining this this majority core, this set of alternatives, is the following. Right? We'll say X belongs to this set if and only if for all other alternatives, it's not the case that Y beats X. Okay, so if you just look at these conditions, you can see that, you know, if X is a Condorcet winner, it beats everything else. So obviously, there's nothing that can beat it, right? So if you're a Condorcet winner, then you're obviously in the majority core. That is, the alternative is. All right, so this majority core idea, it's more relaxed or weaker than the idea of a Condorcet winner. And let's go through an example just to see how the two concepts compare. So here's a profile with 4 individuals and 4 alternatives. And here I'm labeling the columns by the individual. These are not the numbers of people who have these rankings, right? So person number 1 has the ranking A, B, C, D. Person number 2, B, A, D, C. Person number 3, C, B, D, A. And the last guy, D, A, B, C. Okay, so if we think about the majority preference relation that's determined by this preference profile, if we compare A to B, we'll see that it's a tie, actually, right? Person 1 and person 4 prefer A, but person 2 and person 3 prefer B. So I'm not going to put an arrow between A and B. What about A and C? Well, you can see there's 3 people, 1, 2, and 4, who prefer A. Only one person prefers C. So A beats C, according to majority rule. A versus D, well, looks like we have another tie, 2-2. Let's check out B. So B versus C, we have 1, 2, and 4 prefer B. So B is going to beat C. And then comparing B to D, we have 1, 2, 3 people again. Okay, and then C versus D, that looks like a tie as well. So that's the majority, or the graph of the majority preference relation in this case, right? This is our PM. I think this is the first example where we've actually had ties. We have several ties going on here. And if you look at this, you'll notice that there is no Condorcet winner. B is close to being a Condorcet winner because it beats C and D, but it does not beat A, we could make it a Condorcet winner if we switch these preferences here to B over A. Then we would add this arc, and suddenly we have a Condorcet winner. Okay, but let's go back to the original. So there is no Condorcet winner here, but the core is non-empty. There are alternatives that belong to the core. If you look at B, of course, it's not a Condorcet winner. We just established that, but there's nothing that beats it. So that alternative would belong to the core, to the majority core. Okay. What about alternative A? Actually, it's not a Condorcet winner either, but and it only beats C, but nothing beats it, so it also belongs to the majority core. Okay. So the majority core here would consist of A and B. All right. Now, so these are two concepts that are closely related, but the key here is that even though the Condorcet winner might be more intuitive, the majority core idea is really more important for choice. Okay. You could argue for either A or B to be choices that are justified by majority rule because there's nothing that beats either of them. All right. So in terms of making choice, majority core is the important idea. Now, if we continue thinking about majority voting, I will just note that well, I'll give an example. It's a famous example called the Condorcet Paradox that shows that well, we already saw there might not be a Condorcet winner, but even more, there might not be any alternatives in the majority core. In other words, the majority core might be empty or void, and then there really is no straightforward way to make a choice based on majority rule. So in this Condorcet paradox, there are three, in the simplest form, there's three individuals and three alternatives. A, B, and C. And if we do the graph of majority rule here, we'll see that two people prefer A to B, person 1 and person 3. So we have an arc here. Person 1 and person 2 both prefer B to C, so we have another majority preference. But notice that persons 2 and 3 both prefer C to A, and so we also have C beating A. And what we see here is that if you pick any alternative, there's another alternative that beats it. So in a deep sense, there's really nothing choosable. There's no viable choices here. The technical way of saying it is the majority core is empty. If you wanted to write that in terms of mathematical notation, you would say it's equal to the empty set, the set that has no elements. Okay, so this, first time you see it, might be a surprising possibility with majority voting. Majority voting is so intuitive and so common, and with two alternatives, there's no issues. We use it all the time, and there's always a winner. But with three or more alternatives, this is a possibility. And it's not specific to just this setting with three individuals and three alternatives. Okay. With more alternatives, So this will be the first version of the Condorcet Paradox, which is the most famous and simplest one. But we can do this with any number of alternatives as well. Okay, so the way I would set this up is the same. I'll have 3 people. And I'll take 2 alternatives, A and B. And then I'm not even going to worry about the rest. I'm just going to put them all below A and B. Okay, so I'll just have a blob down here. Put them in any order you want. Person 2 is going to have B as their favorite, and then all the other alternatives will appear in the ranking in some order, and then C will be, A will be at the bottom, okay? Person number 3 is going to rank A and B at the bottom. They're going to have all the other alternatives in some order up here at the top, and then they'll have A and B at the bottom. So here I can do kind of a graph of the majority preference relation. I don't know how many other alternatives there are, but I'll just do a blob for those. So in this modified example, there's still 2 people, a majority, who prefer A to B, person 1 and 3. And notice that B beats every alternative other than A and B, right? Because in these rankings, person 1 and person 2 prefer B to all those other alternatives. So we're actually going to have one arc going from B to each other alternative, okay? I'll just draw that like this. But and then the last point is that person 2 and person 3 prefer all of those other alternatives to A, so they are all going to be majority preferred to A. They all beat A. Once again, the majority core is empty, okay? Well, what about more people? Well, that one's a little bit more nuanced because, so this will be the third version of the Condorcet Paradox. If there are more people, so there's more than 3 people, well, we can redo the Condorcet Paradox just like we did, as long as there's 5 or more people. So, okay, what we're going to do is let's just divide or partition this is our set of voters, right? There's n voters in there, and I'm going to divide them up into 3 equal size groups, or at least groups that don't differ in size by more than 1 person. Okay, I'll say roughly equal size, roughly equal size groups. Okay, let's call those groups G1, G2, and G3. Okay, so each group has 1/3 of the entire society. Okay, the reason I'm using this term roughly here is just because of integer issues. If there were 9 people, then I can split these people up into equal size groups. I can have G1 be 1, 2, and 3. I can have G2 be 4, 5, and 6. I can have G3 be 7, 8, and 9. But if there are 10 people, well, I can't divide 10 by 3, and so what I'll do there is, I can have 3 people in G1, 3 people in G2, and then in G3, I'll just put this extra guy, number 10. So the point is that, I can pretty much divide the society up into 3 equal-sized groups, with this one qualification that they might differ in size by 1 person. The reason I'm doing this is because if I take any 2 of these groups, and I put them together, then that will be a majority. That will be more than half of the entire society. So any 2 of the groups together make a majority. All right, so back to the example. I'm going to give everyone in the first group the same ranking. A over, let's do, we can have all the other alternatives in there. So A over B and the other alternatives. Everyone in G2 will have the same ranking, B, and then all the other alternatives. And then A at the bottom. And then everyone in G3, in the third group, will have all the other alternatives at the top. And then A and B at the bottom. So let's do the graph. Put B here now, and all the other alternatives here. All right. If we compare A and B, everyone in G1 prefers A, everyone in G3 prefers A, because those 2 groups are each about 1/3 of the whole society. When we combine them, that's 2/3. That's a majority. And we find that, well, a majority of people prefer A to B, so A beats B. If we compare B to all these other alternatives, everyone in G1 and G2 prefer B. That's a majority. And everyone in G2 and G3 prefers these other alternatives to A. So again, we have this, I should have mentioned this before, this is called a cycle, where we have arrows that, we can start at one alternative and follow arrows and get back to that alternative. That's called a cycle. And once again, the majority core is empty. Well, okay, so we have this Condorcet paradox when there's 3 voters. We have it when there's 5 or more. It's kind of funny to have this sort of intermediate case. What if there are 4 voters? Well, it turns out if there are 4 voters, we can't do what we just did, because then n, it's we're just numbering these guys 1, 2, 3, 4. If we break those up into groups that are as close to the same size as possible, what we end up with is something like this. G1 consists of person 1, and G2 consists of person 2, and G3 consists of 3 and 4. Okay, it doesn't have to be that way, but the point is, at least one of these groups has to have 2 people. But that means the other 2 groups don't actually form a majority. They have only half of the entire society. So, so you can't form a cycle between 3 alternatives here. And so, in this one case, the construction above doesn't hold. However, we're not out of the woods, because if there are at least 4 alternatives, we can do it. I'll just do it with 4 alternatives. and I'll call them A, B, C, and D. And I'm going to form the same kind of preference profile. It's called a Latin square profile, where I have person 1's ranking, and then person 2's, I just take the top one, from person 1, and put it at the bottom of person 2 and shift the rest up. And I just keep doing that, okay, as I go through. And now if I do the graph of majority rule, I'm going to have 3 people preferring A to B, person 1, 3, and 4. 3 people prefer B to C, 3 people prefer C to D, 3 people prefer D to A. Actually, I didn't look at all the other arcs. I suppose we could. What about A versus C? It looks like that's a tie. So, and B and D as well. So we have our majority preference relation. Now with 4 alternatives, we find once again, well, there's no majority core alternative. The majority core is empty. And there's no clear way to make a choice based on majority voting. So this is a problematic aspect of majority voting with more than 2 alternatives. Other than that, majority voting has nice properties. It has it treats people equally. It treats alternatives in an unbiased way. It's also fairly straightforward because it's based on these pairwise comparisons where people can basically raise their hand and say, oh, I prefer A, and the other people say, oh, I prefer B, and that's all the information you need. So it's straightforward to use, but sometimes it just can't be used. All right, what about Borda then? Well, it's, again, it satisfies anonymity and neutrality. Those are the terms that I mentioned before, but it's unbiased with respect to individuals and alternatives. It does not suffer from these kinds of cycles and this lack of applicability of majority rule, because it always generates a ranking of alternatives. So that's a very nice property, actually, and it means that we don't run into these problems. The main drawback of Borda rule that I'll point out is that it requires a lot of information. You need to you're using all the information from each person's ranking. So I'll say the informational requirements are demanding. And so just to illustrate this, let me give an example. This will be an example with 4 different rankings and 9 people. Okay, so first ranking is A above B, above D, above C. Second ranking A, C, B, D. Third ranking C, D, A, B. And the fourth ranking is D, C, A, B. Okay. Now, as I said, there's 9 people, but I don't want to write out, rankings for each one. Let me just indicate that there are 2 people with the first ranking, 2 with the second, 2 with the third, and 3 with the last. And these are numbers of people. Okay. I'm not saying individual 2 has 3 different rankings. All right. So then we can calculate the scores for the alternatives. So for A, that's at the top of the first 2, and it gets 3 points. That's at the top of the next 2. It gets 3 points from each of those guys. It is for the next 2 guys, it's above it's above B, but below C and D. And for the last 3 guys, again, it's above 1, but below 2. Okay, so so that gives us 6, 12, 10, looks like 7. Let's just do this for all the alternatives. And let me just cheat. B gets minus 15, C gets 5, and D gets 3. Okay. So the Borda ranking here is, let's see. So A gets the most, then C, then D, and then B way down with negative 15 points. Okay. So B is the lowest ranked alternative according to Borda by quite a bit. Okay, so now what I want to do is I want to change this preference profile in kind of a small way, but I'm just going to move B down to the bottom of all the individual rankings. Okay, it's already at the bottom of 5 of them, but so I'm going to, for these first 2 guys, I'm going to move B down here and pretend it's not up there anymore. And for the next 2 guys, I'll move B down, and it's not here anymore. So this gives us a new preference profile in blue, and you know, I want to recalculate these Borda scores. Obviously, they'll change because the Borda scores use information about the entire ranking. So if we do it for A first, you'll see that A's position relative to the other alternatives doesn't change. Its Borda score is just going to be the same. It's going to be 7. B now, it's going to be even worse. There's 9 people. There's 3 alternatives above it in each ranking now, so that's going to be a score of minus 27. What about C? So things are different now for C. For the first 2 guys, C is above 1 alternative but below 2. For the next 2, it's above 2 and below A. For the next 2, C is at the top, so it's above 3. And for the last 3 guys, C is above 2 alternatives, below 1. So this is going to be minus 2, plus 2, plus 6, plus 3, which is equal to 9. If we do that for D, let me just fill in the answer here. It's 11. So what we see is, I mean, the Borda scores change. And if we look at the ranking of alternatives, we do that down here in blue. We now see, obviously B is still at the bottom. We just made it worse. But the remaining 3 alternatives, the ones that were in contention, so to speak, D has the highest Borda score, followed by C, and then A. So in fact, of those 3 other alternatives, by moving B down to the bottom, I reverse the ranking of the other three. Okay. This is very extreme sensitivity to these rankings. And so taking this loser and just making it even worse changes the choice for border rule from A to D. Anyway, it's a difference from majority rule, and it's generally thought of as a weakness of the rule, but obviously you get something for it. By using this information, you can generate points for the alternatives, and you always get a ranking. So in this comparison of majority voting and border rule, I wouldn't say either rule is better, but they're just different. And we didn't get into, we don't have enough time to talk about axioms right now. The next step in this process is to move away from looking at individual voting rules and or particular voting rules, and start thinking in a more general way about voting and preference aggregation. We would love, I think, we'd love to have a voting rule that took the best parts of majority voting and Borda. Let's always have a ranking, like Borda, but let's just base it on pairwise comparisons like majority voting, which is just so much simpler. Obviously, neither of these rules give us that. We could spend, a lifetime searching for rules that might give us those properties, like the holy grail of voting. But we're going to see from a more general analysis that would be a waste of time. And I don't want to give too much away. But the next installment, we're going to start thinking axiomatically about voting rules. And that's what's coming up in the next installment. I'll see you there.